sampling. So that is something you can check. But apart from that, whatever are given in the initial pages, all the waveforms you have to generate. You can either use subplot or you can use your own way of representing, but all the waveforms are required, and it should be different than what I have given. So all the waveforms are given to you. You have to make slight changes and you have to mention what is the change that you have done. Suppose I have generated impulse. I'm just giving an example. So all the waveforms you have to change in some way or other. I should not find your code and my code is exact, your output and my output is exact. So all the outputs you have to generate in the same sequence that I have given, but it is somewhat different. Suppose let's say impulse response I have plotted. So I have generated impulse with amplitude 1 at t is equal to 0. So this is a guideline for experiment number 2 writing. Code is given to you, everything is given to you. So suppose I have generated impulse response at t is equal to 0, an amplitude of 1. What changes you can do? You can generate the same thing at t is equal to 0. You can have an amplitude of 5. So you are doing the amplitude scaling. So your output will be different than mine. This is one type of change you can do. Or you can shift the waveform towards right, towards left, or all the things you want you can do. So I have shown one impulse. You have shown five. You can show five impulse. So you can show right shifted impulse, left shifted impulse. You can show amplitude scaled impulse, and all these things. So same thing you can do for step also. I have shown a unit step at t is equal to 0. But from the beginning only, you can show a step of amplitude 10. You can do that. And I have represented all the outputs at in a kind of a subplot kind of a thing. Not necessary. You can separately generate the output and you can show it. So you can use the command figure, and so just you have to mention figure, and then you have to say plot. And so 3 4 waveforms if you're generating, then you can say that figure 1, figure 2, figure 3, figure 4, and plot 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 likewise you can generate. So there should be some change in every uh, waveforms that you have generated. So that is your job. And whatever more important than changing in code is what change you are doing, that you have to mention clearly. Okay, suppose sinusoidal waveforms, I have generated sinusoidal waveform of 3 hertz. You have to generate sinusoidal waveform of 5 hertz. Then you have to show the output between 0 to 2 pi. So between 0 to 2 pi I have shown there are 3 cycles of sinusoidal waveform. Then between 0 to 5 you will be showing 5 cycles of sinusoidal waveform. So likewise I have produced a sinusoidal waveform of maybe amplitude 1 volt. You have to show it for amplitude 3 volt possible. Okay, I have shown a sinusoidal waveform at t. You might show a sinusoidal waveform which is advanced by 3 units or delayed by 5 units, all those things. So 2 works are there. If you see experiment number 2, you have to submit the write-up as soon as possible by Thursday, and already the document is given to you. So those who are not having laptop, it's little difficult for them. So try to get the laptop as soon as possible. Otherwise, you can just hand draw it, and you can submit the experiment. It doesn't matter. Okay, so everything is given to you already. You have to write a bit more, and after writing, you have to submit it. So no excuses, handwritten or typed. Definitely, the typed experiments are not going to get any special care or any more marks or something. No, it is the correctness of your experiment. It is the knowledge. It is the understanding that you show that matters. Whether it is typed or it is handwritten, it hardly makes any difference. At least not to the marking. It will not make a difference. But definitely, if it is typed, it will be easier for you to correct it. So after I give you a correction, it will be easier for you to correct it. And this is going to be a lifelong time document for you. See, whatever document I am showing you now, these are the documents I had generated in 2019. And every year we kept on doing some modifications in all this. But yes, so every year, so whatever notes we are showing, every year we keep on doing some modifications, some addition, deletion. That is possible only if you are having a soft copy. So this soft copy you are not making for me. The soft copy actually you are making for yourself. Okay. So what we are going to do now is for half an hour or 30-35 minutes, I'll be telling you actually some 4-5 circuits. And circuits are very simple. It is a 2-component circuit, RC or RL. So in this case, I think my screen is visible. So the same fundamental has to be used. Question is all the PDFs to be attached. Okay, somebody has asked. 1 second. I want the outputs only. Amruta, you have asked all the figures screenshot should be attached in the PDF. Answer is yes. Okay, so PDFs, whatever document you are generating, even if you don't write the code, it is okay. So only one line you can write in the code. So if you're writing the code, because codes are very small lines, so everywhere clear all, CLC, close all, you don't need to write. That is one thing. So as Amruta has asked, I think it's a good question you have asked. Only thing is small. So all the codes, if you see, it's a 3-4 line code. Okay, so make changes. Waveforms are important, and don't show a subplot kind of waveform after every code. So small code of impulse, and below to that the waveform. So code waveform, likewise you have to go. So the document may become a 50-page document. It's okay, you won't have to write the code that way. Okay, because codes and everything is already written, so a 19-page document is already given to you. Last one, that is whenever you are seeing that aliasing thing, sampling thing, that exactly the way I have done, given usko change mat karo, usko वैसे ही रखो. Okay, only the last exercise in that, so which ends at page number 19. So okay, don't change that, because there are a lot of logic, there are a lot of understanding. वो बहुत time लेके मैंने लिखा था, थोड़ा थोड़ा करके बहुत सारे उसमें understanding है. So it's a same kind of a baseband signal that we have taken. So last experiment number 2, the last code I am telling you, it is mainly to make you understand what is sampling and what is the effect of sampling frequency on sampling. So what we find is, I think I had taken I don't remember exactly, but some frequency I have taken. I think 100 hertz signal I have taken, and then I have taken different sampling frequencies, and I kept on showing you if sampling frequency is 200 hertz. Suppose that is what sampling says, that your sampling frequency should be twice that of the baseband signal. So baseband signal means the signal you want to digitize. Okay, the signal you want to convert into digital. So sampling we are doing because we want to digitize it. So 100 hertz is the signal, sinusoidal signal. We want to digitize that. Then for that, 200 hertz should be the minimum sampling frequency that you have to take. That means only 2 samples you can get in that total time period of 1 by 100 seconds. So that is 0.01. That is 10 millisecond. So 100 hertz means 10 millisecond. So in that, so 100 hertz means 1 by 100, that is 0.01. So 0.01 multiplied with 1000. Yes, 10 milliseconds. Okay, so in that, what you are finding is, so what we'll be finding is, we are taking, if we take 200 hertz sampling frequency, then we are getting only 2 samples. So with that, again, when you are reconstructing, so there are 3 steps. First, we are taking the frequency, then we are sampling it, and after sampling, we are reconstructing the signal in the digital domain. So whatever is the graph you are seeing in all the experiments, all are actually digital domain output. So they are all digitized. They are actually after their reconstructed waveforms. Okay. Now you are finding that if I'm taking 200 hertz sampling frequency, there is some kind of ada theta kind of waveform. It is coming of sinusoidal. It doesn't look like sinusoid. If you are taking 0.001, that is 1000 hertz sampling frequency for a 100 hertz signal, then you might find it's looking somewhat like a sinusoidal waveform. Then I've taken maybe 5000, then I've taken 10,000 hertz sampling frequency. So I want to digitize a 100 hertz signal, and I'm taking a sampling frequency of 10k, that is 10,000 hertz, and you will find that very good reconstruction of the 100 hertz sinusoidal signal is happening. So sometimes the sinusoidal signal will look very sinusoidal like, but towards the tip when the curve is there. Okay, so to produce that curve, you need very high frequency components in the signal. So when sometime if we discuss Fourier series, I'll tell you exactly which part of the frequency band. So higher part of the frequency band, that means maybe 5k, 10k, and all those things. Higher frequencies are actually producing the curvature. So whatever is the curvature at the top of the sinusoidal, you are finding that part. Curve means change. Rate of change is more. That part is actually produced by high frequency signal. And whatever is the rising part of sinusoidal signal, okay, so sinusoidal signal goes like this: rise, then there is a curve, and there is a fall. So this rise and fall, they are produced by low frequency signal, because they are not changing. Whenever there is a change in the direction, whenever there is a change in the curve, that part is actually produced by high frequency signals. So this is actually time to frequency domain understanding. So if you are not keeping the sampling frequency high, then वो जो ऊपर वाला curvature part है, that part actually gets disturbed. So higher value of sampling frequency you are taking, you will be finding that वो top curve जो है sinusoidal waveform का, that will be properly reconstructed. So it is shown that somewhere around 5000 Hz you are taking the sampling frequency. Sinusoidal wave is looking like sinusoidal, but the top is not very properly reconstructed. So as we are increasing the sampling frequency, we are finding that the top is reconstructed very perfectly. So what is the conclusion we can draw from that last part of experiment in experiment 2? That is the sampling theorem and aliasing effect and all those things. Uh, what we find is, if we are keeping very high sampling frequency uh, or sample rate we are keeping very high, then we are finding very perfect reconstruction of the input and the output. So that part you keep as it is, you can study that. So all the waveforms you check, just don't do for preparing journal. Okay, so understanding, development of understanding is very much necessary. So that is what you do. Okay, today now what we'll do is we'll do the experiment number 3, and there are circuits like RL and RC. So RL circuit is called as a first order circuit because there is only one energy storing element, inductor. RC circuit is also called as a first order circuit because there is only one energy storing element, which is the capacitor. And then we will see what is the RLC circuit. So I don't know whether I'll be able to do RLC circuit today or not, but let's see how much we can do. And codes are already uploaded in Google Classroom. So request to all of you is, parallelly whenever you are here, first 10, 15, 20 minutes, half an hour, I'll be explaining this experiment. Codes are given, execution is just single shot type, so I'll just paste the code and run it. So explaining the output is not a difficult task, but understanding what exactly we are doing is more difficult. So by the time I'm explaining, please download all the codes. So 2 files I have uploaded in Google Classroom, please download that. And you can open your Matlab and you can go into that M file creation thing and just stay there. You no need to execute anything because execution is very easy. It is not a difficult thing. Okay, so whenever I'm saying RL or RC, the circuit, base circuit, so it is called as natural response and step response. So this is going to be the header of experiment number 3, and this experiment you have to submit before Tuesday next week because it is very easy. Experiment number 2 and experiment number 3 you have to submit before next week. So experiment number 2 anyway you are submitting by Thursday, this Thursday, and another 3-4 days time you have. So by next Monday you submit this experiment number 3. So this will be having some 5-6 graphs to generate. What is the circuit? Circuit is, we are first giving a Vs supply and you have to assume that this T is closed. Okay, so this path is a closed path. I have not prepared a separate image for this or circuit for this, so you have to understand. So this circuit is closed, so just don't just ignore this switch. This path is connected, you have to assume, and there is a R. So first we are doing RL circuit or LR circuit, natural response. What is meant by natural response? Same thing will be applicable for step response as well. So first what you have to do is, it's a LR circuit or it can be a RC circuit, whatever, and this is connected, so circuit is closed. I am giving some supply for certain time. Okay, so this supply is connected for a certain time, maybe 5 minutes, 10 minutes, whatever. And this inductor stores some energy. And in case of RC circuit, if you are keeping a capacitor here, the capacitor stores some energy. So let me just check whether capacitor is there or not. So this document also I'll forward it to you because based on this document only you have to write your experiment, and these are the graphs you have to generate and show to us. Okay, this is RC circuit, same thing. So I am connecting this supply to this RC circuit for certain time, and then after that I'm removing this supply. So after I'm connecting this for a certain time, this capacitance is getting charged to Vs, because we know that capacitor acts as the open circuit for DC supply. So if you're connecting Vs, let's say 5 volt, this Vt also becomes 5 volt after a certain time when the circuit reaches steady state. Okay, this switch is connected. So after that, let it be RL, let it be RC, I'm opening the switch. So first I allowed the inductor or capacitor. So two different circuit to get fully charged. Inductor stores energy, capacitor stores voltage. We allow that, and after that we open that. We open this switch, we cut this supply, and we connect this R to the ground. So in that case, come to the first page, circuit looks like this. Circuit looks like this. This is called natural response ka circuit. So this was the same circuit as shown previously. L was there, there was a power supply, there was an inductor, there was a resistor, they were in series. I was giving the supply to the RL and supply series circuit, and the inductor had stored some energy. And just check, the inductor had stored energy in the reverse direction, because inductor, as per Lentz's law, it produces a voltage which is opposing the cause of its creation. So this circuit was like this. Inductor was here, and there was a DC supply connected. And after charging the inductor to a certain extent, I removed the supply, and then I connected the L and R in parallel. Is this part understood by all of you? What is meant by natural response and what is the circuit? Anybody, can you just say yes, or I should explain it again? Can anybody confirm? If not, I'll explain it again. Repeat. Thank you. So this is a very simple circuit, R, L and a DC supply. So now listen again, whatever I have said just now, again re-listen it. I kept a R, L, one inductor, one resistor and one DC supply in series initially. I allowed the inductor to get charged, okay, store energy maximum. After I found that inductor has got charged, then I removed the DC supply and I put inductor and resistor in parallel. Then this circuit I have got. Now whatever inductor energy it is there is no external energy connected here. Whatever inductor energy is here, now it will circulate among this RL circuit, which is a parallel circuit kind of a thing, and this inductor will, the energy will come to zero. And in that process, whatever current we get in through this whole configuration is called as the natural response of RL circuit. I'll give you an example. I tell you that some person is there, okay, or some dog is there. I feed him one day with huge amount of food, maybe 10 kilos of food or maybe 1 kilo of food I feed him. Okay, so that is the initial circuit. That is, I give a DC, I give an inductor, I give a resistor, and I give the supply to the inductor and resistor. I charge the inductor, same thing for capacitor also, to the extent. So I feed the dog for one full day with 1 kg, 2 kg of food and all these things. And after that, I suddenly cut the food and I put the dog in a closed door, behind closed door, and I watch him die. That means एक बार तुमको खिलाया, once I have given you the supply, once I have given you the input, and now I want to see how you discharge. So the same thing, how the dog's health change after the food. Okay, so by food I charged him. So here also, by connecting DC supply to RL series circuit, this is looking parallel. You don't have to think this circuit, you have to think the other circuit, you have to think this circuit. Okay, whatever I'm going to show now. So you have to think this circuit. What is that? You have to think this circuit. So initially I am giving this supply to this RL circuit, and after feeding the inductor quite a lot, I chop the DC supply and I make this circuit. And I just check how the inductor current is going to drop, reduce, and comes to zero. So after charging the inductor, so how do I define what is meant by natural response? So it is response of a DC circuit, it is response of a circuit when DC source, which was initially connected to the circuit, is suddenly disconnected from it. And then we check in the source free way, in the source free response, it is written here, in the source free response, how the circuit current changes from high to low. That is actually called as natural response of that circuit. Now the circuit can be RC, the circuit can be RL, the circuit can be RLC. Okay, so here as we are taking RL circuit, initially a DC supply, inductor, resistance, they were in series. I charged the inductor to the extent, and then suddenly I removed the source and I put the inductor and resistor in a closed loop, and I'm checking how the inductor current is going to reduce. It will obviously reduce, it cannot increase because there is no power supply here now. Power supply, it was charged once, so it is like feeding the dog once with a 1 kg of food and then isolate it and just check how its life deteriorates, how the activity of that dog deteriorates. Okay, so the same thing, you will be finding that the inductor current is deteriorating because it is not getting any external supply now. Same thing for the capacitor. So initially RC and DC supply was in series. I charged the capacitor to the extent high, and then I removed the supply voltage from the capacitor, and I found how the capacitor is discharging through the resistor. Okay, so how much is the capacitor current reducing at every instant, and after a certain instant it will come to zero. So this is actually called as a natural response. What is meant by natural response? The way natural means that there is nothing connected externally, no input connected externally. So to run the system, initially you have to connect the supply and you have to charge it, and after you have charged it, remove the supply and see naturally how the response of the circuit decays and comes to zero. Now is it understood? Anybody? Okay. So somebody is saying yes, I think I'll go ahead with it. So natural response. So there are two kinds of response. One is called as natural response, another is called as step response. So for the step response, the circuit is here. So step input is an external input that I'm giving to the circuit. So this is called a step response. Here instead of Vs, I'm giving you a supply. Let's say it's a unit step of 1 volt. So I'm giving a 1 volt, so which is connected, and how it is charging the inductor will be the step response. So whenever I'm connecting an external supply, how it increases the current through the circuit, how the voltage of the resistance increases, how the current in the circuit increases, how the voltage across inductance decreases, because the inductor initially is open circuit. As soon as you connect it in transients, you have seen that as soon as you are connecting at t is equal to 0, the inductor will behave like an open circuit. Okay, and as time goes by, inductor will become a short circuit. So initially if you are connecting 1 volt, that 1 volt will come across inductor, because if it is open circuit means current is 0. So whatever supply you are giving, that whole supply will come across inductor. As time goes by, inductor will slowly become towards short circuit. So as inductor impedance is reducing, current flowing through the circuit will keep on increasing, and as the current flowing through the circuit is increasing, voltage across resistance is also increasing. So finally at the steady state, what you will find is inductor impedance have become 0. As impedance has become 0, inductor voltage has become 0, and resistor voltage is maximum. So if you are giving 1 volt, you will be finding that 1 volt hole is appearing across a resistor, and current flowing through the circuit is V divided by R. Likewise, so that is called a step response. So step response means whatever is the current through the circuit, or whatever is the voltage across resistance, same thing, when step input is connected to the circuit. What is meant by impulse response? Impulse response means if you are connecting an impulse signal to a circuit, then take some parameter in the circuit. It can be voltage across some parameter, some component. It can be current through some component. Okay, so response means what kind of response you want, that you have to decide, whether you want current through the circuit or you want voltage across some component, that you have to decide. Okay, but circuit is responding to the input, that is mainly important. So impulse response means if you are giving the input as impulse, impulse is delta t. What is the Laplace transform of delta t? It is 1. Okay, unit step ut, what is the Laplace transform of ut? It is 1 by s. If a ramp response, I can ask you, because we are doing transfer function. Ramp response means if you are increasing, if you are connecting input as a ramp signal is t. Okay, if you want a higher what is that thing, gradient wala ramp signal, instead of t you can connect 3t. Okay. What is the Laplace transform of t? It is 1 by s square. So if you are connecting 2t input, what will be the Laplace transform? It will be 2 by s square. Likewise. Okay, so I can ask for impulse response of the circuit, I can ask for step response of the circuit, I can ask for ramp response of the circuit. In that case, here in case of Vs, the Vs can be delta t, Vs can be ut, Vs can be RT. RT means RAM. Okay. So here for this experiment, we are going to see two things for two circuit, that is RL and RC. Lastly, we will see RLC circuit as well. So for RL and RC, we will see what is the natural response and what is the step response. Response means how the current decays or how the current builds up in the circuit, that we are going to see. Step response is easy to understand. Step circuit is easy to understand because here we are giving step input, unit step input 1 volt at t is equal to 0. There's a R circuit, there's a L circuit, or there's a R circuit, there's a C circuit, and we are going to find out how much is the current or voltage across capacitor in RC. We're going to find how much is the current through the circuit in inductor RL, likewise. So that is the step response. Natural response is a little difficult to understand. For natural response, also initially we are giving some supply, and when the inductor or capacitor is getting fully charged, then we are going to remove the supply and connect the R to the ground. That means we are providing discharge path for the energy that is stored by this inductor when it was getting charged. So initially we charge the inductor, initially we charge the capacitor, and after it gets charged to a certain extent, we remove the supply and make the RC or RL parallel. Okay, so how does the circuit looks? It is shown here at the top. This is how the circuit looks, but this current I has to be generated because this inductor was charged initially. Then how the circuit is going to discharge, that is going to be the natural response. So we'll start with natural response of RL. So what is the definition of natural response? You have to say that it's the response of a circuit when DC source which was initially connected to a circuit is suddenly chopped off or suddenly disconnected from it, and it is called as a source free response. Okay, so this is natural response. Consider a series RL circuit with initial current through it as I0, okay, and then suddenly it was disconnected. Now I0 is equal to I0. So this is LH and this is R. So this voltage is called as VR, this voltage is called as VL. Okay. Now this proof is not asked in the exam, but this proof you can see. So when I upload this document, you see this proof. Applying KVL around the loop, we get VL plus VR is equal to 0. So this is a loop, and this is VL and this is VR. We can find that in a total loop, net loop voltage across all the components is equal to 0. So you can find out that VL plus VR is equal to 0. So this is a starting point. We are not going to ask you this proof in the exam, but to know it, it's very important. VL plus VR is equal to 0. Now inductive voltage, what is that? L dit dt. Resistive voltage RIT is equal to 0. Take this in the right side and divide by L. So dit dt is equal to minus R by L into T. And then take the integration in both the sides with initial value of I0, because you have found that initial current when the circuit was disconnected, okay, the current flowing through the inductor was I0, and that I0 will decay and that I0 will become equal to 0. So after dit dt, it is at the below, then minus R by L dt. Then you integrate both the sides and initial current was I0. So what you are finding is IT. So this is the last line which is very important. What is called as IT is equal to I0 into e raised to minus RT by L. Okay. So what is this graph like? So this graph is looking like a decreasing exponential. This is very much important. So what is the question? Question is finding the natural response of a RL circuit. So what is the definition of natural response? First, I will charge the inductor. It will store some energy, and then after a certain time, I will remove the supply and I will connect the inductor and resistor in parallel. And then I'll check whatever was the stored energy in the inductor which was producing current I0, capital I0, how is this current decaying and how is this current coming back to 0? How means whether it is very steeply coming to 0 or it is in a very flat manner it is coming to 0. That we are checking. So this is IT. So this is the last line. IT is equal to I0 into e raised to minus RT by L. Or you can say minus e raised to minus t by tau. So what is tau? Tau is equal to L by R. So ये सब लिख के रखो, बाद में याद नहीं रहेगा. Okay, so I0 into e raised to minus capital R into t by L. So take this R below to L. So what you are finding is minus t by tau. So what is tau for a RL circuit? So these questions are asked in the exam. So what is the tau for a RL circuit? It is L by R. That is Henry by Ohm. Okay, Henry by ohm is second. Actually all the time constants are given in seconds. What is the definition of time constant? Definition of time constant is this is the time after which the voltage drops to 63.3% of its initial voltage. Okay, so you will be finding, so at t is equal to tau, if you are substituting, you will be finding it is I0 into e raised to minus 1. And how much is e raised to minus 1? It is 1 by e, so it is around 0.36 or something. Okay, so we'll be finding that after tau time, so if you are substituting this L by R, so L by R is equal to tau, it's a time. Okay, so after the tau time, you'll be finding that current is falling up to 63 point or say almost 64% of its initial current. So initial current was I0. After t is equal to tau, the current will be 0.64 or 0.36 of I0. So you can do all these things. All those things we can show you by definition. Okay, so this is what is called as natural response of RL circuit. So this equation gives that the natural response of RL circuit for DC source is disconnected suddenly. The term L by R. So where is the L by R? So IT is equal to I0 into e raised to minus RT by L. So take this R below to L. So that becomes e raised to minus T divided by L by R. So what is L by R? So for RL circuit, L by R is called as a time constant. So the term L by R is called as a time constant of RL circuit and denoted by symbol of tau. Tau has its units in second. So whatever you are finding, so this is I0 into e raised to minus t by tau. I'll make it a little big. Okay. So e raised to minus t by tau, I think is visible properly. Okay. So you are finding that IT is equal to I0 into minus RT by L. So what is the natural response of RL circuit? The answer is the natural response of RL circuit is exponentially decreasing kind of a characteristic. So after you charge inductor, suddenly you are closing it a circuit, R and L are in parallel, and then how the inductive current decays. So answer is the inductive current decays exponentially. But exponentially how fast or how slow, that depends on the value of tau. Okay, so if the tau value is very small, in that case we will be finding that the decay will be very fast. Likewise, we will see if the tau value is big, at that time decay will be slow. So the voltage across resistor is given by IT into R, so I0 into e raised to minus t by tau. So actually you have found out what is the current in the natural circuit. What is meant by natural? The word natural means there is no force, there is no external force, or there is no external input connected to it. Okay, so a teacher is not there in the class and you 60 people are in the class, you are shouting, you are dancing, you are doing this, that, so that is the natural response. Teacher is the forcing function. As soon as teacher comes, you try to show that you are a very decent people and you behave. So what does the forcing function doing? Forcing function is actually keeping the circuit response within a control, and the circuit is getting steered, or circuit is behaving the way the forcing function is acting. If the forcing function is sinusoidal, the current in the circuit also will behave like a sinusoidal fashion. If the forcing function is a step, the current in the circuit also will increase in a step manner or something. So depending on the forcing function, the circuit response is guided. But if there is no forcing function, if there is no external input, as we are seeing in this case, so initially we had connected a forcing function, we charged the inductor up to a certain value, and then we removed that forcing function. So after we are removing the forcing function, then how the circuit behaves, that is called as natural response, and we are finding that RL circuit behaves like a exponentially decreasing kind of a thing in its natural response, and the formula is I0 into e raised to minus t by tau, where tau is equal to L by R. So you are finding VR. VR is nothing but the voltage across resistor. This is R into IT. IT we have found that I0 into minus t by tau. So that is equal to I0 into R into e raised to minus t by tau. So this is the resistive voltage. So VL plus VR is equal to 0. So if this is the VR value, then VL value is negative of that. So you are finding that as soon as there is a natural response, we will find that the resistance voltage will keep on being positive, and inductance voltage will keep on being negative. Okay, so resistance voltage will keep on increasing or something. So resistance voltage and inductance voltage, they are reverse. So this is what you will be finding. So all these graphs we will generate in Matlab. So it was charged initially up to a certain value, the inductor, by some external forcing function, and then the forcing function was cut, and we are checking how the inductive current is falling. you are going to find this is the way the inductor's current is falling. So this the name is RL circuit natural response. And two more things, voltages you can check. The red voltage is the inductive voltage, it is falling, and the blue voltage is the resistive voltage, which is increasing. But the initially inductive voltage was positive high, so it is coming from positive high to 0. Initially the resistive voltage was negative, and then from here it is coming to 0. But nevertheless, inductor voltage is reducing and resistive voltage is increasing. All these graphs we can see because it is coming from the equation, and there is only one equation, so we will produce the graph in MATLAB for this thing, that is I0 into e raised to minus RT by L. And what happens if we are changing the different values, L by R value if we are changing, so we will do the coding there, we will be changing the value of L by R. That is time constant, we will keep on making smaller and bigger. Okay, if you are making time constant smaller, we will be finding that the fall is very fast. Okay, and if you are finding that L by R value is big, okay, the time constant is big. So time constant big means the circuit output does not change fast. Okay, so a person with very high response, okay, very high response, good response means he responds in very smaller amount of time. In that case, we can say that a system which responds very fast, that means as soon as the input is given, it is producing the output. In that case, it is said that the system time constant is very less. So lesser is the time constant, faster is the system response. ये सब लिख के रखना चाहिए और you have to understand that. So L by R value should be as less as possible if you want the system to be faster. Likewise. So now what you are finding is MATLAB graphs. So first we are finding what is the inductive current graph, then we are finding what is inductive voltage, what is resistive voltage, and all those things. So all these graphs we will generate, and then we will generate this graph. Okay, so this is a very important graph, and we are finding that. So even if I explain this thing to you and leave it, you should be able to generate this graphs because code is same. You are finding that there are three graphs. One is the black graph, one is the blue graph, another is the red graph. So initially this was the inductive current, so this is the value of I0, and after, as t is going on, at t very high, the system is going into steady state, and that value of current is going to reduce. But in case of red, you are finding is very fast it is falling to ground, so almost in 1 second time it has become 0. For the blue graph, which is the second graph, you are finding almost after 2.7 seconds it has fallen to 0. And for the black graph, you are finding almost after 5 seconds the inductor has come to 0. So these are three different circuit responses. Okay, these are three different circuit responses for different value of L by R. So you can say for keeping with R constant, I actually am decreasing the value of L. Okay, so as I am decreasing the value of L, system is going from black towards red. This you have to understand. I am decreasing the value of L means I am making the time constant lesser and lesser. As I am making the time constant lesser and lesser, I am finding the system fall or output fall will become fast. So when black is there, that means here L by R value is more. That means L value is more. Suppose R is equal to 1, R we have kept constant. So this is a graph for changing L, keeping R constant. Now somebody will say, sir, I will keep L constant, I'll change R, no problem. So in this case, as you are increasing the value of R, you are going from black to red. So net aim is tau should be decreasing. So tau should be decreasing. Either you keep L constant, you change R, or you keep R constant, you change L, or you change both. Doesn't matter, but T value is decreasing. So as T value is decreasing, we are coming from black towards red. So lesser is the time constant, faster will be the fall. So here it is written smaller is the time constant tau, faster is the decay. So this is called actually decay because initial current is I0. From I0 the current is falling to 0 ampere. Okay, so y-axis is RC circuit natural response, current amplitudes likewise. And as I am increasing the value of R or as I am decreasing the value of L, I am going from black to the red. So higher values of R or lower value of L will cause lesser time constant, and the time constant will be lesser means red graph and the system will be faster. So keeping L value constant. So here they have kept L value constant, R value increasing. We are going from C to L. Somebody can say I will be keeping R value constant and I'll keep on decreasing the L value. There also you are decreasing the tau. There also you are going from black to the red. So here system output will reach to final steady state value, zero value. So zero value is the steady state value. So just after initial charging, you had some energy stored in inductor. You removed the forcing function, and then you are checking how that inductive voltage or that current actually falls through the resistance, and it comes to zero. So this R is kind of called as a discharging resistance. So this R is actually creating a discharging path for the energy which got stored in the inductor. And how fast the decay will occur, it depends on the value of R or value of L or value of L by R. For three different circuits, you have to generate three different graphs. So system response is red is the fastest, and system red is with smallest time constant. R value is the highest for system red. On the other hand, the system black is reaching zero value very slowly because system black is behaving with bigger value of time constant. So smaller value of R, system black is slower system. Same thing you can do for a RC circuit. So the same thing that initially this RC and a supply voltage was series circuit, RC and V supply. There was a series circuit. Then I charged the capacitor up to the certain voltage, and then suddenly I removed the supply and put C and R in parallel. Then how the capacitor is getting discharged. So how this voltage is falling to zero. So in case of inductor, it was current which was falling to zero. In case of RC circuit, it will be this voltage, capacitance voltage, which will fall to zero. So how to prove it? Initially, we had taken VL plus VR is equal to zero. In this case, what we are saying is with respect to this node, though it does not look like a node, but we can find that IC and IR, there are two currents, and IC plus IR is equal to zero. Okay, because here you can assume another third arm, and the third arm is having current zero. So let's say input current is equal to zero, which is coming in the third arm. Okay, so that current is zero is equal to outgoing current IC plus IR. So whatever is the incoming current to this node is equal to zero, it is coming from the top. Let's assume an outgoing current is equal to IC plus IR. Hence IC plus IR is equal to incoming current is equal to zero. Then substitute IC, that is C dVC dt, IR VT by R, and you just exchange the variables. So finally what you are finding is natural log of VT. So VT is nothing but the voltage across the capacitor, or VCT you can say, minus T by RC, natural log of A, and then you find out what is VT. So VT is nothing but the capacitor voltage, how it is getting discharged. So this is equal to A into e raised to minus T by RC. So what is A? A is nothing but whatever was the initial voltage that was stored in case of in the capacitor. So whenever you had initially charged it, suppose the capacitor got charged up to voltage A, so that charge will keep on reducing, and that charge will keep on reducing with a exponentially negative or exponentially decreasing kind of a graph. So at t is equal to 0, you are finding Vt is equal to A. So substitute e raised to minus T by RC, substitute t is equal to 0. So e raised to 0 means 1. So initially Vt is equal to A. Just now you have removed the supply, just now you have made C and R parallel. How much is the voltage across capacitor? It is A, capital A. Okay. That is the initial condition. That is what they have said. At t is equal to 0, V0 is equal to capital V0 at t is equal to 0. So V0 is equal to A. Now as time goes by, that A will decay to 0 because the time constant in this case is R into C. So RC circuit time constant is R into C, unit is second. Inductor RL circuit time constant is L by R, not R by L. Okay, so it is L by R in case of inductive circuit. Current is falling there. In case of capacitive circuit, the time constant is RC, and it is falling exponentially. Now we will be seeing the graph, same graph as we had seen. So you are finding that Vt is equal to A into minus T by RC. So if you substitute, so RC is the time. Let's say R and C value we have added in such a way that so R is equal to 1 ohm, C is equal to 1 farad. So how much is the time constant? 1 ohm into 1 farad is equal to 1 second. So I'm challenging you all. You can just can prove it. It's very easy. Just prove that 1 farad into 1 ohm is equal to 1 second. So take it as an assignment and prove it, and just write it in a page, 2-3 line ka proof hai, and send it to me by WhatsApp. Or L by R, that is Henry by resistance, that is ohm. Henry by ohm is equal to second. This is the first proof you have to do. And second is R into C, that is ohm into farad. is equal to second. So these are two proofs you have to do, and you have to write in the just in a small paper, and you can send me what's happening. So in case of RC circuit, it is R into C, that is ohm into farad is equal to second. You have to prove that. In case of inductive circuit, L by R, that is Henry by ohm, it is also is equal to second. You have to prove that. Very simple. Students do it in one day or so. Just do that and send me. So tau is equal to RC. So what is the RC deciding? You can see here in this graph. So in this graph, the proof will not be asked. Only you remember this, that Vt is equal to A into e raised to minus t by RC. That is, A is the initial voltage. You can take A value as equal to 1, doesn't matter. But main important thing is e raised to minus t by RC. So RC is equal to tau. Tau is the time constant of RC circuit. So this voltage will decrease in a exponential manner, okay, and it will come to zero. So that is what we are going to see. We are going to see that graph, and we'll be finding that IR is equal to Vt divided by R. So how much is the circuit current when the capacitance is discharging? So you can see here. Previously, in case of inductance, you had found that inductive current is reducing in an exponential manner. In case of natural response of RC, you are finding that capacitors voltage, see the y-axis, RC circuit natural response, capacitor voltage is reducing in a exponential manner. So in this case, you will be finding that as capacitors voltage is reducing, capacitance current will be increasing. So the red one is the resistive current and the blue one is the capacitive current. So this is one thing you have to remember. As the capacitance voltage comes to zero, capacitance current will be increasing from negative to zero, and the resistive current actually is reducing from positive 1 to the 0. Likewise, so this red one is the resistive current, and the blue one is the capacitive current. So whatever data is being given to you, so this file also will be forwarded to you. Do the graph through your Matlab and see every part of it in a very proper manner. Now this is one graph. There is a basic graph we have to generate, and then we will generate this graph. So here we are saying three different circuits with three different RC. Okay, so RC natural response with three different time constant. Can anybody tell me in which case tau is low and in which case tau is high? So what is tau in case of RC circuit? It is R into C. So bigger is the value of tau, slower is the response. Slower is the response means the decay will be slower. So in this case, the R decay is slower. Okay, so in this case, the value of tau will be more. So if you are keeping C constant, let's say for all these three circuits, C is constant. So in this case, this red is having R value very high. So RC value is very high. In blue case, R is medium. So RC value is medium. And in black case, R value is least. Let's say in the first case, C value is 1 farad. Let's say here, R is equal to 5 ohm. So 5 ohm into 1, time constant is 5. In this case, let's say R is 3 ohm. So 3 ohm into 1 farad, that is 3 seconds. And in this case, R is equal to 1. So 1 ohm into 1 farad is equal to 1 second. So this might be 5-second time constant. So R into C is equal to 5 seconds. In this case, R into C is equal to 3 seconds. In this case, R into C is equal to 1 second. So both these graphs you have to generate. And whatever graphs I have generated, your graph should look different. So here you can use a legend command. Here it should write that red R is equal to this much, blue R is equal to this much, and black R is equal to this much. So you know how to produce the legend output. You have done MATLAB courses. We have done in previous experiment also. We have used legend command. So whatever legend you want to display here, that legend should come in the output. So that is a change you will be doing in the output. So all the graphs, the legend should be there whenever you are comparing 2 or 3 graphs together. So here I am finding the RC natural responses with 3 different time constants. So if time constant is more, RC value is more. In that case, the decay will be slower. If RC value is less, the decay will be faster. So it is saying that. So remember, red is right and black is left. So smaller is the time constant, faster is the decay. Tau is equal to RC. Hence, for the smaller value of R and C, the time constant will be lesser. That is the black graph. So RC value less, it will be falling faster. That means it will be coming faster to the steady state. So in case of natural response, steady state is 0. Okay, so black will be coming faster to the steady state. This will be having less settling time. So in the second order circuit, we'll be finding settling time. So and the system will be faster. So faster system output will reach to the final steady state value, 0 value, faster in time. In the above graph, system response black is fastest as it is reaching to the zero value fastest. So this is sharper decay response. System black is with the smallest time constant as R value is smallest for this system, provided C is constant. On the other hand, system red is reaching zero value very slowly. This is called as a flatter response. So both all are exponential, but exponentially e raised to minus t by RC. So if RC value is more, the fall will be lesser likewise. So t by tau likewise. So you can find out. So on the other hand, the system red is reaching zero value, other things like this. So these are the things we will be checking in the our experiment also. We'll be producing all those graph and we'll see how exactly it happens. Now we are coming to the step response. The same thing. Here the proof is also given. What is the step response? So we are giving a step input. In that case, you are finding that response. So instead of so circuit is shown to you first. So first I'll show you the circuit, and proof is there. So don't worry about the proof. So step response means I am giving the input to the circuit as step. So it's a RL circuit, and in case of RL circuit, I think circuit is given at the top. So step voltage of RC circuit. A step voltage of RC circuit means the same circuit. So I think circuit diagram is given below. Let's check. This is actually the step response of RC circuit. I told you. So this step response of RL circuit. So instead of L, if you are just keeping a C, and you are taking across the C. So in that case, this is the step response of RC circuit. So I think I have not generated the diagram for step response of RC. Let me just check. So the diagram is not there. I'm sorry for that. So it is a very simple circuit, that is resistance, capacitance and supply all are in series. So in that case, whatever supply you are giving, whatever voltage you are giving a step, unit step. That means you are connecting a 1 volt to the input of R like this and C like this. So voltage, R and C, all these three things are in series, and output we are taking across the capacitor. Okay, so when I send you this document, before that I will generate a RC circuit step response, or it's very easy to understand also. In the next circuit, whatever I have shown, in case of inductor, you assume there is a capacitor and voltage is taken across capacitor, and what you are finding is VT. That is very important. VT is equal to Vs plus V0 into Vs into e raised to minus t by tau. All the thing we have to understand, what is VT, what is Vs. So VT is the nothing but instantaneous voltage across capacitor. So there is resistance here, there is a capacitance here. So this capacitance is getting charged through the resistance. Okay, and RC is called as a time constant. So if the resistance value is very high, in that case capacitance will get charged very slow. So it's a supply here, there is a resistance here, and there is a capacitance here. So this capacitance is getting charged to the resistor. So RC means it's a time constant, means how fast the capacitance will get charged. So if the R value is very high, that means less current will flow to the circuit. The capacitance will take more time to charge. So that is the significance of actual time constant. So if RC value is more, means capacitor will eventually get charged to the same voltage. So if you are connecting 5 volt here, capacitance will get charged to 5 volt, but in maybe 10 minutes time, if the R value is very high. So RC is actually equal to time constant. If R value is equal to 0, how much is the value of tau? Tau is equal to R into C. R value is 0, so tau is equal to 0. That means as soon as you are connecting the supply across the capacitance without any resistance in between, instantly the capacitance will get charged to the initial value. So here there is a 5 volt, here there is a resistance value is 0, and here there is a capacitance. So as soon as you are connecting the 5 volt to the capacitance without any resistance, that means resistance is 0, instantly the capacitance will get charged to 5 volt. Okay, so then because RC is equal to 0, but there is a very big chance that as soon as you are connecting a very high voltage to the capacitor, capacitors might blast as well. Okay, that's why we control how we want to charge the capacitor, and how the capacitor will get charged, it is given by this graph, and we have to actually plot this graph. Vt is equal to Vs plus V0 minus Vs into e raised to minus t by tau. Now what is Vs? Vs is the supply voltage. Supply voltage means if you are connecting a unit step means 1 volt. That time Vs should be equal to 1 volt. What is meant by V0? This is very important. Okay, so whenever you are doing this kind of experiments, you should know all the parameters. What is tau? Tau is nothing but R into C. So you have to first define how much is the R, how much is the C, and you have to again plot the same graph for different values of R and C, different combinations of R and C. Three combinations are important. One is fastest, one is medium, one is slowest. So keeping C constant, if you are increasing the value of R, you will be finding that the graph is getting faster. So if you are keeping the RC value less, in that case you will be finding that capacitance is charging very fast. What is V0? So Vs is the supply voltage for 1 volt step or 2 volt step, 5 volt step. You are giving step response, means simple DC you are giving. Step input is nothing but it's a DC voltage. So 20 volt you can give, 10 volt you can give, does not matter. Charging time will be time constant is remaining same. Whatever voltage you are connecting, that has nothing to do with time constant. So time constant is a inbuilt property of the circuit, how fast it is going to charge. That is given by R into C. So whether you connect 20 volt or you connect 200 volt, the response curve will be having the same shape. Size will vary, but shape will be same. What is V0? V0 is if the capacitance is holding some charge initially, and V0 can be positive as well as negative. Okay, so we will see the effect of V0. If you are keeping V0 initially is equal to 0, then this whole equation becomes Vs minus Vs into e raised to minus t by tau. Initially relaxed system. What is meant by initially relaxed? Initially relaxed means V0 is equal to 0. The capacitance is not holding any charge from the beginning. So in that case, whatever supply voltage we are giving, that supply voltage is causing all the output change. So in that case, it will be Vs minus of Vs into e raised to minus t by tau. So if you take Vs common, it will be 1 minus e raised to minus t by tau. Likewise, but if initial voltage is there, so this is the general formula. Okay, so this formula you should understand that Vs is nothing but the step input. V0 is the initially stored voltage in the capacitor, and this V0 can be positive, negative, both. And in Matlab, very easily you can find out what will be the response if V0 is positive, V0 is negative. So it's a very funny thing, we will see that. If the initial voltage V0 is equal to 0, so this is the general formula, you have to plot this formula only. If initially V0 is equal to 0, then you are finding that it is Vs into 1 minus e raised to minus t by tau. So this is a formula we are more habituated with. If it is RC circuit, I ask you it's a RC circuit, how will the capacitance get charged? So your answer will be, sir, if Vs is the supply voltage, it is Vs into 1 minus e raised to minus t by tau. Why? Because we are assuming that initial voltage V0 is equal to 0. That system is initially relaxed. But if it is not, then you have to write the V0 here. So that is a very important thing. So what is Vt? Vt is equal to Vs into 1 minus e raised to minus t by tau at time greater than 0. So likewise, it will keep on going. And we are going to find how much is the current in the circuit. That also we can find. So Matlab graphs. What are graphs we are going to find? Output capacitive voltage graph. That is, output is increasing. Graph is Vt plus V0 minus into e raised to t by tau. Decreasing current graph. So as the capacitance voltage is building up, eventually we find that at steady state in the RC circuit, there is no current flowing through the circuit, because we say that capacitance is open circuit for DC. Okay, but initially the capacitance was short circuit. This you have to understand, because initially the rate of change of voltage was very high. Okay, so and this capacitor wants to oppose that. So whenever in transients also you might have seen that initially just now you have changed the switch, just now you have connected the step input to the circuit. Initially the capacitance is short circuit, so maximum current flows through the circuit. So what was the circuit current? It was input divided by R. So current was very high. As the time is going by, capacitance is becoming a open circuit. As it is becoming an open circuit, what we find is the capacitance voltage is building and the circuit current is reducing. So you will find that capacitance voltage and capacitance current, they are actually opposite in nature. Capacitance voltage will keep on building up, and capacitance current or the circuit current or resistance current will keep on decreasing. So decreasing circuit current we will find, increasing capacitance voltage we will find, and decreasing resistive voltage. So resistive voltage and circuit current, these two graphs are same, because VR is equal to R into IR. and IR is equal to IC. So as IC is reducing, IR also will be reducing. So you can find it here. In the next graph we have shown. So this is the red graph is how the capacitor's voltage is building up. So whatever code I have sent you, if you run that, this codes you will be getting. This is how the capacitor's current is reducing. So red is the capacitive voltage and blue is the capacitive current. Okay, so they are opposing in nature. Capacitor's voltage is building, capacitor's current is reducing, and you are finding this is the RC resistive voltage response, because resistive voltage response will be same as the voltage or current in the circuit. So as current is reducing, resistive voltage also will be reducing. So this black and this blue, they will be having the same fall, because this fall is nothing but fall of IC or IR, and VR is equal to R into IR. So whatever is the fall of IR, whatever is the gradient of IR, that will be same as gradient of VR. Now the same thing, I'm showing you three graphs. Okay, so this is the first graph, red. This is the second graph, blue. This is the third graph, black. They are with different RC for step input. So input is given like the step. What is meant by step? At 0 directly it is going up and is like this. So step input is, it's going up like this. This is the input and like this. So this is the step input. But for step input you are finding that this red is not following the step input in a proper manner. Black is trying to follow the step input in a proper manner. Okay, so the black is closest to the step input. How much is the error? ये जो error दिख रहा है, ये जो black के पीछे जो area दिख रहा है, white area, this is actually the error between input and output. And that area is more in case of blue, because how much is the deviation between input and output? Actually, the output should follow exactly input. I am teaching you so that you can get 100 marks. But somebody has got 90. So how much is the error? This much is the error. How much is the error? 10. That means 10% you could not follow me. Some student is getting 60. That means 40%. So iske piche jo area hai, this is the area. Okay. This is the area of error between output and input. So input is the teacher signal. Output is what student is getting in the exam. So this area piche beside the blue is the area which is the error. And red is giving the biggest error, because red is very slow, and as red is very slow, it is taking quite a lot of time for the red to follow the input. So almost after 10 seconds you can find the output is touching the input. So input is 1 unit step. Okay. So the blue is touching almost after 4.7 seconds the input. So input is 1. Okay, the black is touching the input almost after 2.5 seconds. Likewise, so black is the fastest system, that is lowest time constant, RC value is lowest. Blue is little faster, so RC value is little higher but lesser than R. R is slowest. Okay, so likewise you are going to find voltage response for 3 different time constants. Same thing happened in RL circuit, but in that case it is current. Okay, same thing, exactly same response. So here you are finding for capacitive circuit the output voltage. So whatever output voltage VT graph. So VT is equal to V0 plus VT is equal to Vs plus V0 minus VT into e raised to minus t by tau. So this is the equation you had got in the previous page. Likewise, so this graph, VT is equal to Vs. Vs is the supply voltage. V0 is the initial condition minus Vs into e raised to minus t by tau. So in this case, you are finding that the graph is starting from 0 and going up to 1. Whatever graph just now I have shown you, the common 3 graph. That means here V0 is equal to 0. So we are assuming that V0 is equal to 0. If it is V0 was suppose 0.3 volt, then this graph would have started. If V0 was 0.3 volt, then this graph would have started from 0.3. But it would have gone up to 1 only. It cannot go up to 1.3 because we are charging the capacitor up to maximum 1 volt. But as it was storing 0.3 volt inside it initially, this graph would have started from 0.3 and it would have gone up to 1. So all this I will show you while we are doing this Matlab programming. What is the effect of V0? It can be negative, it can be minus 1. So if you are putting V0 as minus 1, then this graph will start from below 0. So this graph will start from minus 1, and after a certain time it will go to plus 1. Okay, so whatever is the initial voltage V0 you are talking about, that will be your starting point at t is equal to 0. So the same thing will happen in case of RL circuit. So this is your finding RC step response with different time constants. Initial voltage, it is shown here, you can check. Initial voltage is 0.7 volt. Okay, the same graph, initial voltage is 0.7 volt. So see that all the graphs are starting from 0.7. So the same fastness or slowness you are finding, but this red is actually starting from 0.7 and going up to 1. It is 1 because input is 1 volt only. It cannot cross 1 and it cannot go to 1.7 because we are starting, we are giving the supply of 1 volt only. So the black is actually starting from 0.7 and it will go also up to 1. So this is how the capacitor behaves. Now there is a negative minus 0.4 volt, you can check. So it is starting from minus 0.4 and it is going up to 1 likewise. So this is the effect of initial voltage stored in the capacitor. So whatever is the initial voltage stored in the capacitor, that will be the starting point of the output graph. So smaller is the time constant tau, faster is the rise time, faster is the rise of the voltage as tau is equal to RC. Hence for lower value of R, keeping C constant, the time constant will be lesser. As time constant is lesser, waveform will be faster. It means that system output will reach to the final value. So in the natural response, what was the final value? Final value was 0 because that was the steady state. In case of step response, because step response means step voltage is like this and it's staying at 1. So final value of the output should reach to that 1 value. So steady state is at 1 or whatever. If you are giving 5 volt, steady state is at 5 volt in case of step response. Okay. But in case of natural response, the final value was 0. RL circuit step response. Exactly same thing happens in RL circuit, but instead of voltage across capacitor, it is current through inductor. Okay, the same thing. And initially Vs is given, T is closed. Exactly at T is equal to 0, inductor was open circuit. Okay, so how much was the inductive voltage initially? Inductive voltage was very high, all the inductive voltage. As the time is going by, inductive voltage becomes 0 because inductor becomes a short circuit. But initially, all the voltage, whatever you had connect, it had appeared across inductor when exactly the T was closed. So resistance voltage was equal to 0. As time is going by, the circuit is going towards steady state. Current is building in the circuit. IR is increasing. IR is same as IL, and VR also is increasing. So inductive voltage is reducing, but inductive current is increasing. So in this case, previous case RC circuit, the parameter was VC. In this case, the circuit parameter is IR or IL. Okay. So the same way you had seen that capacitor's voltage was building, in this case you will be finding that inductive current is building likewise. So this is what it is said, inductor at T is equal to 0 and inductor at T is equal to infinity. So at T is equal to infinity means steady state, the circuit is acting as a short circuit. Inductor at T is equal to 0, it was like open circuit, that's why it is shown as a current source. Current source is having internal resistance of infinity. So initially this was an open circuit. Okay, I0 was equal to 0. At T is equal to infinity, the current in the circuit is high because this inductor has become short circuited. So all these concepts are put here. So IT is equal to, so final proof is not given. Directly I have given you the answer. So IT is equal to I0, that is Vs by R. Sorry, Vs by R. Vs is the supply voltage. I0 is the initial current. So if the inductor was holding some current into it initially, so when I had connected the inductor, already it was having some current stored in it from its previous operation. That actually is called as I0. Okay, minus Vs by R into e raised to minus RT by L. Again the same thing, R you have to take below L, and L by R is the tau for inductive circuit. So the same way we will go and we will find that IT is equal to Vs by R. So Vs by R is nothing but Is plus I0. I0 is the initial current of the inductor stored. Vs by R is called as Is. So this Vs by R or Is component is what is created due to supply input. S stands for step. So Vs stands for step voltage. So that is a forced response. I0 is the initial response. Likewise, it going. So again the same thing, we are finding that plot IT, I0 is equal to Vs by R. So IT is equal to Vs by R 1 minus e raised to minus RT by L if I0 is equal to 0. So initially capacitor inductor is not having any stored current. Initially a relaxed system, that is there is no initial current in the inductor. In that case, inductor current will build like Vs by R, that is Is into 1 minus e raised to minus T by tau. So tau is equal to L by R. Likewise, Matlab graph. MATLAB graph, what we will find is, we will finding that inductive current is increasing like this red. It is said that inductive current is increasing in a red fashion, and because inductive impedance is coming from infinite to zero. Okay, and as inductive impedance is coming from infinite to zero, you will be finding that inductive voltage is actually falling, because at t is equal to infinity, inductance acts as a short circuit and voltage across short circuit is zero, and current across short circuit is maximum. So you are finding that if you are giving a step input, what is meant by step input? Suddenly you have given from 0 to 1 and like this. So step input is goes at t is equal to 0 plus to 1 and stays there forever. So this red or this current, inductive current, is trying to follow that unit step input whichever is given. How much is the error? Error is whatever is the area shown in the left side of the red graph. Okay, and if you are increasing the if you are decreasing the time constant tau L by R, at the time this red will keep on shifting to the left side. So this red graph will keep on going closer to the unit step input. So that control is in our hand. R and C we can design likewise. And RL response, so this is actually the main response, RL current response. So you can see a resistive voltage. Okay, this is actually resistive voltage amplitude. Resistive voltage will be same as the circuit current. So whatever is the circuit current response red, and this resistive voltage response also will be the same. So main response is this red one, and now in the next we are going to produce three red waveforms like this. Okay, so this is the red response, there is a blue response, this is the black response. In this case we can find that this red response is having highest value of L by R. Okay, so L by R is nothing but the time constant. So keeping R constant, you can increase the value of L. So this is the highest value of L, that is the red graph. This is the lowest value of L, that is the black graph. And black graph is the fastest, because you can find here it has reached to final value almost after 11.5 seconds. And this blue and red, they will take quite a lot of time. Actually they have got saturated, they are not increasing anymore. Okay, so that process has become very slow. So in this case we can find that this L by R value or time constant for this black graph is quite small, hence it is increasing very fast. But time constant for this red graph is largest, and blue graph is medium, but blue and red graph are quite slow, whereas the black graph is quite fast. Likewise, all the discussions are given below, I think it will be giving. And if the initial current you have taken something, so initially you are taking that I0 value as something. So in this case, you have taken the I0 value as something like, so it will be written here, I think 0.3 or something. Okay, initial current I0 is equal to 0.3. In that case, you will find that the inductive current will start building from 0.3 and it will go up to the maximum value, whatever is the maximum value, 2. Okay, so that was the initial part. And if the current is minus 0.4, you will find here, so inductive current, initial current is minus 0.4, that means inductor was holding a current in the negative direction, that is also possible. Then the initial graph will start from minus 0.4 and then it will go up to some value of 2. Okay, likewise. So all these graphs we have to now generate. This is the last thing. So RLC circuit, step response and all we will do some next day. We will see the RL and RC only today. So we are having another half an hour in our hand. So 8 to 10 minutes for each graph we will see. And you have to generate all these three graphs for each cases. Okay, that is RL natural, RC natural, RL step, RC step, and with initial condition, without initial condition. Just follow all this, see the code and try to match this theory with the code, then you'll be able to understand. So smaller is the time constant, faster is the rise of the inductive current. Tau is equal to L by R. Hence for higher values of R, the time constant will be lesser, the system will be faster. It means that system will reach to the final value input step in faster in time. So lesser is the value of time constant, faster will be the response. So I will now launch the MATLAB. Okay. So just give me a time. I will launch the MATLAB, and you also launch the MATLAB and go to the code. So download first code from Google Drive, Google Classroom. So this is MATLAB online. So you go into MATLAB and so MATLAB online, and at the same time so let us first do the natural response of RL. This code you have to copy. Let's first do the natural response of RL. So I've shared my screen. It'll come in certain time. So I've shared my entire screen. I'll remove my image. So I think you can see my codes. So this code I have copied. So this is the number 3 in the page number 3. You can see. So I have opened this code. So I have sent you 2 documents. So this is the first document, natural response RC. So first page, that is next is step response of RC. Third page I have got is called as natural response of RL. So we are doing the first order circuit only, and then go to MATLAB. Go to MATLAB online. So the previous this code is still there. If you are not able to see my window, please let me know. So this is something has come. What I'll do is I will take a new thing. I will take a new and I will save it. Anybody saying anything? If there is any problem, just let me know. This is untitled. I will remove. Sort of half wave rectifier I'll remove. Now saving. So saving I will say it RC nat RL. I will say. Okay. I'll save it as nat RL. Okay. Anybody please respond if the code is visible to you or not. Just say yes or no. I cannot see my Google Meet window.
It's
Somebody just say
visible,
in
sir.
a voice if my code is visible to you or not. Is it?
Yes, sir.
Okay. So I can explain it now, right? I think all the codes and everything is visible to you. So I'll go to view. There was some facility I could increase fonts. Is it visible bigger little?
Yes, sir.
So previous one was better or this is better?
This is better.
Fine. So how can you do that? So you have to come to home. Okay. Then you have to go to this preferences. Right side. I think you can see my screen, right? My cursor movements and everything.
Yes, sir.
Okay. So go to preferences, click that, and here a lot of preferences you will be finding. So whatever is the color, command history, command window, and all those things. So here you can find this thing. So this is the font. It initially it was 10, now I have made it to 14, and I have done the apply, and okay. So now see, so clear all, close all those things are same. Now t is equal to, so I'm just explaining you, t is equal to 0 to 0.01 to 16. So this is the sampling time I have taken, and I0 is equal to 1. I0 is the initial current. I0 I have taken as 1. Okay, so initially I said that the current will start from 1, because this is natural response. So you have to start from somewhere. Here you cannot set as 0, because initially I told you that this is a natural response, means first we have to charge the inductance, so that there will be some initial current in the inductance, and that value has to be something, and then how the inductor current will fall from that initial value to the 0 value, that is called as natural response. So L is equal to 1, R is equal to 1, all these things we have kept. Tau is equal to L by R, that also we have said. So IL is equal to I0. I0 is the initial current. So don't confuse between natural response and step response. Sorry. So step responses first have to charge it to some value. So that value I'm saying as 1. Now I0 is equal to e raised to minus t by tau. So tau is equal to L by R. You can see that I will keep on increasing the value of L, and I will be getting a flatter kind of a response that I will get. So I have used your subplot 211. What is meant by 211? 21 means 2 row 1 column. That means actually I will be plotting 2 graphs, because already I have defined it to be 2 1. 2 1 means I will be defining 2 row 1 column. So that means there will be 2 graphs only I will be plotting. Out of that, this is the first graph. What is the first graph? It is the inductive current. So inductive current is nothing but IL. IL is equal to I0 into e raised to minus t by tau, that I will be plotting. So x-axis is time, y-axis is current amplitude. Title RL circuit natural response inductive current. Legend inductive current. Okay, so this will be given in the first graph. So you can say this is the first graph, and you can say this is the all about second graph. What is the second graph? VR. Okay, so VR is nothing but the how much is the voltage across the resistance. It is I0 into R. Okay, so the same thing, I0 is flowing through R. So the same graph, just multiply by R. So this is the only difference. And if you are multiplying R with IL, you are getting actually VR. Okay, and VL is equal to minus VR. So you can plot both. You know what is VR, and you know that VL is equal to minus VR, because I had shown you that inductance and capacitance resistance, they are actually forming a loop, and the net voltage in that loop is equal to 0. So if voltage across resistance is VR, voltage across inductor will be minus VR, that is equal to VL. So this is a subplot. VR is given in red and VL is given in blue. So this is the grid on. Grid on means you will find what is the grid in the graph. So X level, Y level, title, resistive voltage and inductive voltage graph. Legend, resistive voltage is given by red, and inductive voltage is given by blue. So all those things you can find. Now I'll just save it. So to do that, you have to come to editor. One is home, another is editor. So all the run command and everything is there in editor. So I went to home because I wanted to change the size of the font. That I have done. Now I have come to the editor and I have saved it, and then I will run it. God forbid the output should come, it should not get stuck. Yeah, so there are 2 graphs. The first graph will be of, so there is 211 and 212. Is this visible? Anybody?
Yes, sir.
So these are 2 graphs. You can click on the figure. So first you will be finding that RL natural response, it was starting at 1. Remember this 1, I will show you the change. And this is the legend. So how to use legend I have shown you. So inductive current they are showing. So it was starting at 1 and it is falling now to 0. And you will find that the resistive voltage also is starting at 1. So as current was 1, R value was 1. If you see the code, R value was 1. Okay, and the initial current is 1. So just see that this R value we have kept as 1. As R value is kept as 1, whatever is the initial current, this is I into R1 is equal to V. So this red is actually the resistive voltage. So I is equal to 1, R is equal to 1. So V is equal to 1 initially, and you find that VL and VR, they are opposite to each other. So if VR is positive, VL will be negative. So this was negative. So it is coming like this. So I think this graph is understood. Only what I'll show you is if I make initial current I0 as 5, then see what happens. So previously it was 1. Now you can check here. This graph was 1. It was starting at 1 because I0 was equal to 1. Now what I'm going to do is, so I'll remove this graph first. Now I have made this initial current I0 as 5 ampere. That means whatever initial charging you had done, so this is natural response, whatever initial charging you had done, that had generated an initial current of 5 ampere in the circuit. Okay, now you can check that this is the starting point of 5. Okay, resistive voltage also is becoming 5. So which point you have to change? So the same graphs you have to generate, but again I'm telling you, output of this experiments should be different for everybody. So I had generated for 1 ampere, but you have to generate for any other thing. Okay, you can change the value of so now remember this curve. Remember this curve, that is R is equal to 1. So it is L by R. Let us increase the value of L up to 10. You just remember the slope. Okay, how it is. So it is coming down quite fast. Now I have made L is equal to 10. So L by R is the time constant. Now you will be getting a flatter waveform. Flatter means it will go towards right, and sharper means the blue will come towards left. Okay, now I have made L is equal to 10. Let's see what I get. Okay, so now I want a slower time constant. So that's what I have increased the value of L by 10 times. Let's see what happens. So I have taken L as 10, R as 1. Now let's see what happens. See that it has become very flat. It is not going to zero very fast. This is how the value of tau changes. So if you are increasing the value of tau, that time the graph becomes very flat. Previously it was coming down to 0 almost at 4 seconds. Now it is going very slow. Now what I'll do is, now I'll make it, initially it was 1, now I'll make it 0.3. Okay, so it will become faster than the initial thing. Okay, so save and you run it. So initially it was 1, L is equal to 1. Then we have made it 10. It was becoming very flat. Now we are becoming 0.3. See that? See that? It has become quite fast. Okay, so fast charging. So almost at almost 1 point, let's see how much it will be showing. 1.48, almost 1.5 seconds, it has come to 0. Okay, so this is how you have to show the effect. And VR and VL also changes accordingly, because this VR exactly following the curve of the I circuit. Okay, so what all changes you can make? You can make changes in I0. I'll take it back to the initial thing, and I will. You can change the value of L. You can change the value of R, and likewise. So this is called as RL natural. Then I'll go for the same graph, but not other things. 3 graphs together. If I plot the 3 graphs together, then what happens? That I will show you. So I will use the same thing. I will use the same Matlab file number name. So I plotted it. I put it. So CLC clear all, close all. Now I am plotting it from 0 to 7 seconds. So let it plot by 10 seconds. Okay, 7 seconds also, no problem. I0 is equal to 1. So initial current I am taking as 1. So what I'm doing is I am actually comparing 3 different time constants. So first time constant tau is equal to 1, because L by R1, we have chosen the value of R1 same. Sorry, R1 value is differing 1, 2 and 5. L value is kept as same. So I gave you a question that L by R is equal to a tau, L by R is equal to second. You have to prove that. So please give it a try. So this is how I'm finding out what is the natural response of 3 different time constants. So L is 1, R is 1, time constant is 1. L is 1, R is 2, tau is 0.5. And L is 1, R is 5, tau is 0.2. Okay. So in the third case, it is I3. So you can say I3 is given by red. So red means smallest time constant. That means it will be fastest falling. Here I3 is red, it is the smallest time constant. So I2 is medium, I2 is given by blue, and I1 is given by black. So I1 is having bigger time constant, that is 1 second. I2 is medium time constant, I3 is smallest time constant. Remember that? And initial current is 1, that also you remember, and then run it. So I3 is fastest, red, and I1 is slowest, black. I think this is stuck. This will not execute, it seems. On karo. So again, save it and make it. So I am reducing this sampling. So 0.01, I have made it 0.1. This will reduce the calculation by 100 times. Now it will come very fast. Let's see. See that? Okay. So the black one is the slowest you can find. So here I can find that I1 is black. Black is the slowest. So that's why it is taking quite a lot of time to come to 0. Almost it is taking 6 seconds. Then you are finding here R2. R2 is blue, so blue is in middle, and the fastest one is red. So if you want, you can see it in a bigger fashion like this. Here the legend should come, but it is not coming. They have mixed like this. So in this case, you are finding that this black one is the slowest response, and the red one is the fastest response. Likewise. So what you can find out is what is meant by time constant. So time constant is 0.5 or time constant is 1. This is something. So let us see what is the meaning of time constant. So for slowest graph after 1 minute, after 1 second. So slowest graph, what is that? Where is the code? Okay. Slowest graph, okay, minus t by tau, 0.5, 0.2. So where is the graph? Likewise. Okay. So this is for natural RL. Now I will go for RC. So the same way you can do for natural RC also. So I have shown you natural RL and I will show you the step response of RC. That will be more interesting. So natural of RC and forced of RL will be same kind of graph. Don't worry. So I'm not going to use it anymore. I'm creating a new script and workspace and everything. So here you can again go to home and you can change it the layout. Layout is 3 column. Likewise. So you can go to this layout. So come to home and come to layout. You can mention default. If you are doing default, it will come back to the original thing. So come to this layout, 2 window, 3 window, all these things you can show. So if you click default, it will be giving you the original thing. So what I'm going to show you now is what is the step response of RC. So first I'll save it. So go to the editor, so command window, take the command window like this, and come to the editor and save. So I'll give is step underscore RC. Likewise, and I will explain the code first. So are you all with me? Are you all with me? Is it visible? The code is visible to you. So now it is gone. Just give me time. Matlab is refreshing. Okay, Ashutosh, thank you. Code is refreshing and will come. Amruta, admit, left the meeting. Okay. Okay. So now it has come like this. So I think we are having time up to 11:50. So right. Okay, so step response of RC. So CLC, clear all, close all these things are there. T is equal to 15. So 0 to 15. I will reduce the workload on Matlab. So I will make this 0.01 as 0.1. Okay, so this way I am increasing the fastness by 10 times. Initial voltage I am keeping as 0 volt. So V0 is equal to 0. C and R initially kept as 1 and 1. So here I am actually plotting RC step response for a single circuit, and I'll be showing you the here this is the IR. Okay, so IR is equal to VS by R and exponential minus T by tau. So there are this is the actual formula that we are plotting for. That is capacitive voltage is equal to supply voltage Vs. Supply voltage, how much are we giving? Uh, Vs plus V0 minus Vs into e raised to minus T by tau. Okay, likewise. So V0 is equal to 0, initial voltage I am taking as 0, and Vs I am giving as 1. So let us first plot this and then we will play with it. So this is the first VC, capacitive voltage. IR is equal to Vs by R. So if you change Vs, the current flowing through the circuit also will change. Current flowing through the circuit will be initially very high. As the time goes by, it will come to 0. And capacitive voltage initially it will be very low, and as time goes by, it will reach to the Vs. If we are giving Vs is equal to 1, final value of Vc will be equal to 1. And below I am plotting VR. So I am plotting three curves. One is VC, like this. It is written here, capacitive voltage. So here VC is red and IR is blue. So how the current is changing with respect to VC. So IR is same as IC, the same thing you can say. And next I am plotting as VR. So it is again a 2-1-1-2-1-2 thing. So that means I am going to plot. So editor, save and run like this. So we'll plot. So what we are doing is step response of RC circuit. So externally we have connected a step voltage, and we have connected a step voltage of 1. You can find out. So this capacitor also is charging to step voltage of 1. This is the first thing you have to see. So red is the capacitive voltage and blue is the capacitive current. So you are finding that initially the capacitance was short circuit. That's why current was maximum. So as time is going by, capacitance is becoming open circuit. So that's why this current is falling. So capacitors voltage and capacitance current, they are opposite in nature. This is the first thing you can find. And whatever is the circuit current, that is same as the resistive voltage. So shape of blue and shape of black, they are actually same. This is the first thing you have to understand. Now let us play with it. So now first thing what we will do is we'll change. So two things we will change. We will change the okay, one thing at a time. So instead of VS10, we will keep VS as 3.76. So supply voltage will be giving us 3.76. So let's see what happens for that. So editor, save and then run. Editor, run. Okay. So we have made supply voltage as 3.76. No change we have made in R and C value. They are the same. So here tau is equal to R into C. So if you are increasing the value of R and C, the graph will become slower. Now you can change. It is 3.76. Now it is not 4. So here if you bring your cursor, it will be showing you what is the value. So it should be closer to 3.76. So you can find here 3.75969. So x is equal to 9.4 and y is equal to 3.76. Likewise. So initial current also for capacitor, you can find this is also, this will be also in the range of 3.76 because R is equal to 1, x is equal to 0, y is equal to 3.76. That is the initial current. So this is how Vs is affecting. Second thing what we'll do is we will change the value of R. So we'll make C as let's say 1.5. Okay, we'll make it faster then. So make C as 0.3. Okay, so RC, we have reduced the value of C. That means we'll be getting a faster waveform. Let's see whether we are getting it or not. So if you remember the curvature in the previous case, now in this case, if we are reducing the value of C, that means the charging should happen faster. And it is 3.76 only we have kept. the charging should happen 3 times faster. See that? Okay, so previous time the rate was quite, it was taking quite a time to go up. Now in this case, the rate is going up very fast. Likewise. Okay, and now what we'll do is this all the other things changes equally. Now what we'll make is we'll keep this Vs as 4. Okay, so or we can make keep it as 2, R value another thing, and you can keep, so here you can make the change V0 you make as 0.6. So the initial voltage we are changing. So V0 we have made at zero point 0.6. So previous case it was starting from 0. The amplitude graph of voltage was starting from 0. Now we have made initial voltage as zero point 0.6. So C is still less, R is still more. So time constant we have changed. Supply voltage is 2. Supply voltage is 2 means final output voltage of the capacitor will be 2. You can see here. Okay, the capacitor is going to 2 finally. But what is the starting point? Starting point from the red graph is you can find here. Okay, so this is the starting point, and if you take the cursor here, you will be finding that y is equal to 0.6. So at t is equal to 0, y should be is equal to 0.6. It should show, see here. Okay, so at t is equal to 0, y is equal to 0.6. So this is the starting point of the red graph. This is very important. Okay, so if you change the axis very clearly, you will be able to find out what is the starting point. Okay. So here we are starting the graph at t is equal to 0, not at 0, because we have changed the starting voltage. The starting voltage we have taken as 0.6. But the final voltage is 2 only. Finally, it will go to 2 only, but starting point is 0.6. There's one thing you have to see. Second thing, the charging has become fast. Now let us make charging slow. Okay, so now I will change it to suppose change the thing slow, though this is 1.5, R also is equal to 1.5, Vs equal to 2. Starting point I'll make as 0.67. Let's see how it happens. So now starting point is negative because capacitance is charging some voltage in the negative direction, 0.67. I have made the graph slower, so 1.5, 1.5, that means I have made the time constant as 1.5 square, so that is around 2.25. And Vs is equal to 2. So all these changes you have to make, and you have to put all these images in the graph. And every person should have a different graph, because whatever changes you are making, other person is not knowing. So you can make changes in initial voltage. So initial voltage, 2 waveforms you have to generate, that is with positive initial voltage and negative initial voltage, as I am doing it here. Okay, and you have to change the time constant. You can change the supply voltage Vs. So this is actually the step input. You are giving a 2 volt DC, and all these cases. So I have made it slower. I have taken a negative negative initial voltage, and I have made the waveform slow. So it will go to 2 volt, but it will take quite a lot of time to reach to 2 volt. See here, starting point is negative. So if you see a cursor here, see that it is starting at 0. It is minus 0.67, because you have kept the V0 as minus 0.67. So it is starting at minus 0.67, but it is going up to 2. There is no doubt about that. And this current is also reducing. This current is not starting from this current is starting from 1.33. So all these calculations, if you put it in the equation, initial voltage is 0.67 minus, you will find that initial current also will be 1.33. That is not a problem. And the graph has become more flatter. You can see it has become more flatter because R and C value we have changed. We have made it bigger, so the time constant has become bigger. And the last graph we will see, there is a comparison of 3 graphs together. So this is also RC response like this. So I will remove this very fast. We will do it. We are having only 1 minute time in our hand. So the same RC response, but for 3 graphs. Okay. So here we are plotting for 0 to 12 volt. Initial voltage you are taking as 0. If you want, you can change it here only. So initial voltage let us take at 0.8, and Vs let us take at 1.6 likewise. So we are starting all the graphs at 0.8 volt, because we are assuming that the capacitance is having initial voltage of 0.8, and supply voltage is 1.6 volt, and there are three cases. First case, it is Ra into C, so Ra is zero point 0.5, and C is C value we are changing actually. Sorry, actually Ra, Rb, Rc value we are changing. I'm sorry, we are actually changing the Ra value, and C is constant. C is equal to 1. So first case, it is the fastest waveform because Ra is smallest. Second case, it is little faster, sorry, little slower, and third case, it is slowest. So whenever Ra is Rc, Rb, Ra, so they are nothing but resistance A, resistance B, resistance C. So third case is given by red. So red is slowest, blue is medium, and black is fastest. So the rise of black will be very fast because time constant is small. So smallest tau, it is written here, smallest tau fastest. There's a legend, and whatever parameter you are defining first, Va, that will be taking the first legend. Okay, and whatever is the VB, that will be taking the second fast, this thing, moderate, and last one. So let us run this. So go to editor and run this. So three graphs we are going to find. V0 is 0.8, Vs is 1.6. So we'll start from 0.8. You can find here we are starting from 0.8. Okay, and we are going up to output voltage of 1.6. This is the first thing. Second thing, black is the fastest. You are finding here black. Black is having 1 into zero point 0.5, that is 0.5 second time constant, and red is having very high starting constant, that is 2 into 1, that is 2 seconds. So red is the slowest waveform and black is the fastest waveform, and both all three waveforms are touching to final voltage of 1.6, and they are starting from 0.8. Let's just see one thing. Let us change the initial voltage and make it from minus 0.4. Okay, all other things we are keeping constant, so just one change, that is we are starting from minus 0.4. That means whether your capacitor is storing positive voltage or negative voltage, uh, in both cases you can generate the graph. So here you can see here it is starting from minus 0.4 and is going up to 1.6. And if the waveform is produced, so this legend also should come here clearly. As it is online, it is not coming, so you don't have to worry for that. Main thing you have to check that there are three waveforms, and all the waveforms are started from minus 0.4 and they are going up to 1.6. So I have shown you one step response, that is RC step response, and I have shown you one natural response, that is RL natural response. So 2 and 3 I have done. One is natural response of RC. You can do it on your own, and two types of graph you have to generate. So there are total 8 codes given. If you check for natural response of RC, one separate graph and one combined graph of 3. Okay, so this calls for 3 graphs total. So first graph will generate 2 graphs, 2 1 1 2 1 2, and second graph will generate 1 graph, like this. And then again second, that is step response of RC. So first graph will generate 2 for one circuit, and next graph will generate 3. So likewise every circuit, RL natural, RC natural, RL step, RC step, everything is having 3 graphs. Okay, so total 12 graphs you have to generate, and all the values should be different than what I have, and you have to submit this write up. So code you need not write, code you should have with you, because all the codes are very properly generated. And write up should be having a little bit of theory. So theory also I will post, whatever I have explained today, theory I will post. So theory and explanation of graph with whatever changes you have made in that, that you have to show, and that will be it. Okay, so this is all from my side today. I'll be posting this theory to you as soon as possible, and that's all. You can log off, and thank you. That's it from today itself.